Well, good morning, class. It is Friday of our first week of the summer quarter, and I was going to finish up the week with a lecture on matter and density. So, hopefully, you have downloaded these lectures and you are following along. Hopefully, you are familiar now with the objectives that we like to create. We're going to talk about the three states of matter. We're going to classify pure substances, mixtures, elements, and compounds. So just a little vocab for us today. And then we're going to talk about this concept of density. And then we're going to continue that conversation about conversion factors. And so density is a way for us to convert back and forth between mass and volume, but it's also used as a formula. And so this just gives us another opportunity to talk about that dimensional analysis, that conversion of units, and that sort of thing. So I think a lot of these topics are just sort of that job training. We are talking about matter in chemistry, and so we want to just kind of give these definitions. We're going to talk about all kinds of different things here, and so this gives you just a little bit of foundation, which we will continue to expound upon as we go through the course. So if I ask you a question about what is matter, the scientific definition of matter is anything that takes up space. So anything that takes up space and has mass. And so when we say, so I challenge you to sort of think about things that don't take up space or have mass, right? So often students will tell me that air is not matter, but it definitely has what we call volume. That's another way to say space, right? And mass, this is something that we would measure this maybe in our base unit of liters. And mass, we spoke about yesterday, we measure that in grams. So anything that takes up space and has mass is called matter. Air definitely is matter. It does take up space. It does have mass, although it's hard to measure air into air, but it can be done. There's a lot of things that take up space in our life, like love and those sorts of things. But basically, there's a long list of things that you can come up with that are not matter. So I challenge you to sort of think about those things. Okay. So when we talk about three states of matter, perhaps you are familiar with what they might look like. So it's nice to kind of look at a picture here, what a solid looks like. And I'm going to write down H2O, and I'm going to use a little parentheses to say that that's solid. If we melt that solid ice, we call that ice maybe, basically then we get H2O, and we'll use a little parentheses with an L for liquid, and then we can go H2O G for gas. But I want you to really contemplate, like, how are these things alike and how are they different? The first way they're alike, hopefully you'll notice, is that they're all made of the same stuff. And so I'm just going to point out, and I think everybody knows, that H2O, it looks like this. It's got an oxygen particle and two hydrogens attached to it. There's a specific shape to it, which we'll get into later. And we'll explain why that shape is that way. But I want you to notice as you go through, like melting this ice and then putting it into steam, right? We might call it steam. And we often call this water because it's just so prevalent in our life. We actually call it the universal solvent, but we'll get to that too. But the idea here is how are they alike? Well, they're all the same types of particles, right? But when you think about it, right, the amount of energy and the spacing and the organization of the particles is going to be very different. So the energy is different because in order to get from a solid to a liquid, we have to melt it, which means we have to add heat. And we will talk a lot about that too. We have to add heat here as well. And we will give you names for that later on. If I want to go the other way, if I want to condense the steam to make it to liquid and want to freeze the liquid to make it into ice, I have to remove energy. And so the energy is a big deal. The spacing between the particles, between particles, and the organization. You'll notice that in a solid, the organization is very rigidly held in position. It's very organized. The particles are close together, and then when you get into the liquid form, there's a little bit of chaos in there, but they're still sort of touching each other, and then lots and lots of space between the particles here in the gas form. And we will spend a lot of time talking about gases later. I just want to mention I'm using water because it's just such a great example, but we can freeze and melt and make, and make into gas many other substances, okay? But we're much more familiar with water, and so that's why I like to use that as an example. Some of you might know that solid carbon dioxide doesn't go through the liquid phase, it just goes right to the gas phase. We call that sublimation, and we'll talk about that later as well. Okay, so lots of stuff goes between phases, solid, liquid, and gas. States of matter, I just use the word phase, and that's another way to talk about states of matter. All right, so when we talk about the 3 states of matter, solid, liquid, and gas, and some of you guys are familiar with, there's one more called plasma, which is kind of an ionized gas, and we're not going to talk about that in this class. Okay. We want to talk about stuff called, when we study matter, okay, we talk about physical and we talk about chemical properties, okay? So physical properties, when we talk about that, those are things like the color of the matter, the phase, the odor, the density, which we'll talk about in a second. What I like to say when we talk about physical properties is if you think about your driver's license, I always have trouble spelling this word. Yes, I think that's right. Does it go the other way? Anyway, so when you think about how we would describe you as a person on your driver's license, it's going to give you your height, your weight, your gender, your eye color, your hair color, blah, 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 right? So those are your physical properties. Your chemical properties, which is harder to go with, but basically, so it's when we bring these substances together, when it's brought into contact with other materials, how does it behave? Okay, so things like solubility. Does it dissolve? Okay. Is it flammable? Okay, flammability is a chemical property. And so when we talk about physical properties, we're talking about sort of like how would we describe it? And then chemical properties are how does it react, right? How does it react? And we will spend a lot of time talking about reactions and that sort of thing. Okay, so physical properties, chemical properties. We can use another set of words that seem really familiar, but physical change and a chemical change, okay? I just want to make sure we understand the difference between that, right? So a physical change is going to be the change in state or phase, right? And we've already looked at that. We said water goes from solid to liquid or back again, right? That's a physical change. And again, what we noticed is the substance's organization, the substance's, the molecule itself, the substance doesn't change. It just gets, farther apart or closer together. So if we looked at that, that's a physical change going from one state or phase to another. However, in a biology class very soon in your future, you will take water, liquid, and you will put little electrodes in it. You're going to do this little electrophoresis where you're going to separate out the DNA particles. And anyway, what you do is you do it in a water solution, and you'll actually see the bubbles of hydrogen and oxygen being formed. This is a chemical reaction, and I'm going to balance it because it'll bother some of you if I don't. And we get these gases over here. So basically in a chemical change, what we do is we are breaking down, we are changing the materials into something different. Okay, basically let's say it this way. We're gonna rearrange the atoms to create new substances. And those substances are going to have different chemical and physical properties. Okay, so the difference between a chemical change and a physical change is important for you to understand. And we will spend a great deal of time talking about this as we go forward. So the first sort of practice here, I just kind of want to hone in on that idea. So classify each process as a chemical or physical change, right? So dissolving calcium chloride in water. I'm going to save that one for a minute and let's just go on to the next one. Burning gasoline, the word burning. Basically, anytime there's we call this combustion. When you burn a hydrocarbon, okay, if we burn a hydrocarbon, we're going to combine it with oxygen. And if it burns completely, we're going to get carbon dioxide and water. And so that is definitely a chemical reaction. So this is definitely chemical. Anytime you see the word burning, you're combining with oxygen, and it's always going to be a chemical reaction. The word right here, the key word melting, heating wax so that it melts. Basically, you're taking wax in the solid phase and you're making it into the liquid phase. And basically, we're not changing anything about it. This is definitely a physical change. Okay. Calcium chloride and water dissolving is kind of an interesting thing. Calcium chloride, we'll learn, is this. When we put it in water, it's going to create ions. And we'll talk about that later. So this is kind of one of those first example of a gray area that we're going to run into. Okay, but the fact that we're breaking this particle apart, we could classify it as a chemical change. But the fact that it goes back together, if we evaporate the water, we might say that's a physical change. So again, I'm going to just say that in this class, you will find that there are shades of gray. Okay, so we definitely have burning being a chemical. We definitely have melting being a physical, and then dissolving calcium chloride in water can be classified as somewhere in between. Okay, so we'll kind of follow up with that later as we talk about ions in solution. I know students hate that. Okay, a little bit more vocabulary. Basically, we will talk a lot more about these things. A pure substance, okay, a mixture. And then an element and a compound. So an element and a compound. All right, so let's talk about these words. So when we think about a pure substance, I know you've used the words pure before when you've referred to water, I think. So pure water, pure oxygen, right? If I take salt, I can have pure sodium chloride. So a pure substance is a unique substance. It's one type of particle, okay? Water, we just said, is a molecule that looks like this. And if I just have only water molecules, I have a pure substance. Even though there's hydrogen and oxygen involved, which is what confuses people, right? There's hydrogen and there's oxygen involved in this. But because it's attached and there's only that type of molecule present, that would be a pure substance. Same thing with oxygen, right? Two particles of oxygen stuck together make pure oxygen. And our third example here is sodium chloride. This is just salt, table salt, that you put on your food to flavor it, right? And it's a sodium attached to a chlorine. And again, it's pure, and it's confusing because there's two substances there, sodium and chlorine, but they're connected together. And when they're connected together, they're a single type of molecule. And so we can classify those as pure substances. Okay, so pure substances, all right? What happens though if I take that pure, I'm gonna draw, and you guys are gonna see what a great artist I am for the first time. So I'm gonna take a beaker, ooh, that's amazing, and I'm gonna put water in it. Okay, so I have pure water. And maybe you've done this before, perhaps when you cook your pasta, perhaps when you've had a sore throat and you've gargled with warm salt water, you've put saline in here, right? You've put salt in here. And as soon as I do that, I've created a mixture, right? So now I have two pure substances. I have this pure substance and this pure substance, but I have them put together, and I'm going to call them a mixture. Now, what makes them a mixture is what I was speaking about before, right here, when I said, if I evaporate the water, I can get them back. They are not chemically bound together. They are together, and they're in the same space, but they're not connected chemically, meaning they don't have a bond between them, okay? Things like trail mix, that's a really good example. Trail mix is a really good example of a mixture, right? Trail mix, however you make it, probably some nuts, maybe some chocolate, maybe some dried fruits or whatever. It's mixed together, but you can physically separate them. Okay, so we'll say that can be physically separated. That's what makes a mixture a mixture. Okay, so when we talk about a mixture, We have two or more, because we can put more, two or more pure substances stuck together, but basically they are not bound chemically. That's the big kicker, okay? Not chemically bound. So we'll put that in there, not chemically bound, meaning there's no bond, okay? No chemical bond, and we will spend a great deal of time talking about that. Okay, an element, it's pretty easy. An element is basically anything that you find on the periodic table. So these are substances made of only one type of atom. Okay, and the periodic table, which we will talk about next week, the periodic table, they are on the periodic table. It's called the periodic table of elements, right? And so big idea there is elements are one type of atom, okay? So actually oxygen can be classified as an element, and they are all represented on the periodic table. Okay, compounds. So the last one is a compound. We've talked about a whole bunch of them already. Water, sodium chloride, carbon dioxide. Those are all compounds. They are one or more atoms chemically bound together. Okay, so basically big idea here, and what makes them different from a mixture is these guys are attached. They've got bonds between them, and if we want to break them, we have to do chemistry. Okay, a compound is chemically bound together. That makes them hugely different than these guys over here. Okay, so making sure this is going to come up a lot. So just be sure as you go through here, pure substance, mixture, element, and a compound. Okay, and so kind of honing in on that idea, here's a little bit of practice for you. So this says classify each of these. This is molecular art. We're going to know a pure substance, a pure compound, or a mixture. Okay, so basically if we have a pure element, we have a single type of atom, right? And so if I were to color code these, because this is in black and white, there's 1, 2, 3, 4, 5, 6 atoms here, and they're all the same type. So we would maybe, and they're only one atom, so we're going to call this a pure element. Okay, this one right here, you can see perhaps there's two atoms bound together here. Maybe that's oxygen, maybe that's oxygen, maybe that's oxygen. And I think this is methane, CH. This is CH4. Basically, we'll talk about that later. But there's two substances here. So this would be a mixture, if you notice. Okay, we've got both oxygen and CH4 in here. And so basically, we've got two different types of molecules, but they are not chemically bound together. So that makes them a mixture. Over here, we've got a whole bunch of methane, right? CH4. You don't know that, but that's okay. I'm going to tell you that. And so this is a pure compound, right? It's a pure substance, if you will. We can call it a pure substance. And they're getting a little bit more specific in this question, asking if it's a pure element or a pure compound, okay? And then over here, last one, we've got 1, 2, 3, 4 atoms of one type, and then we've got 2 atoms of another type. And so basically that means this is going to be a mixture also. What makes this different is this is a mixture of elements, right? And this is a mixture, you could say, perhaps of compounds, although oxygen is really an element. So it could be an element and a compound. I think I just made that confusing. Okay. Anyway, the point is, can you tell the difference between a pure element, a pure compound, and a mixture? Okay. We'll continue to talk about that as we go through here. Okay, so sort of the last, well, there's 2 more concepts to get to here. One of the properties of matter that we talk about, it's an identifying property, is density. And so when we ask the question, what does it mean to say that something is dense? Basically, I think you probably know what density is. I mean, it's kind of a funny question, and I know you've probably heard it before. Which weighs more, a pound of feathers or a pound of lead, right? And I don't know if you've ever heard this before. It might be an old thing, but the point is, which weighs more, a pound of feathers or a pound of lead? And the answer is, well, they both weigh the same. They have the same mass, but their volume is going to be dramatically different, right? Lead's going to be more dense because basically we have much more mass, in a small area. I'm going to try to write better. I'm sorry. Much more mass in a small area. Right? Feathers, if you think about a pound of feathers, it's going to occupy a lot more space because there's a lot of air in between. It's not dense. And so density has to do with how much mass is occupied in a specific volume. And the density formula is kind of interesting. You know, we defined matter earlier today as anything that has mass and takes up space. So when we talk about density, density is a measurement, a sort of a dual measurement of both mass and volume. And often we will use the units of grams per milliliter. So density has to do with how much mass is packed into a specific volume, into space, right? So think about things that are dense. Think about things that are not dense. And so they have heft to them, all of them do. So basically, think about the difference between a shot put and a softball, right? They're about the same size, volume, but they're definitely dramatically different in mass, right? And so that's how that works. It turns out that the density of water is 1 gram per milliliter. And we will actually be using that later on in the quarter to do some calculations and some work. And I know all of you have probably witnessed the fact that oil floats on water, right? You've made oil and vinegar dressing, or you've put oil into we're going back to your pasta again, you've put it in your pot of pasta. It turns out that the density, let's try that again. The density of oil is 0.93 grams per milliliter. And you can probably see this being less dense, right? It's actually going to float on top of the water. And that's kind of why they do that. I have a graduated cylinder sitting on my desk in my office where I am not today. And if you look at it, it's got water on the bottom and then it's got oil on the top. And so you guys, I'm sure, have all seen this before, right? It's a good thing because when oil gets spilled, unfortunately, in the ocean, right, basically it floats on top, which is easier for us to remove it. Not that it's easy to remove, but it's thankfully it's there. And I live out here in Anacortes by I don't live by the refinery. I'm kind of away from the refinery, but the refinery is front and center in the town of Anacortes. And when those big tankers come in, you'll notice when they're unloading them, they put these big sort of floating baffles all around them to try to prevent any sort of leaking of oil into anything further away from the refinery. It's kind of interesting. Okay, so basically what I want to point out here is, density is a dual measurement, and it is a sort of a measurement of how much mass is packed into a specific volume. Okay, we can actually use density as a conversion factor. I'm going to show you that. So I'm just going to show you how that might work. We've kind of given you just off the cuff here a couple of densities, but I want you to see how that can be used as a conversion factor. Okay, so let's just say that in my graduated cylinder right here, I had, 35 milliliters of water. And I wanted to know what the mass of that water was. And I mentioned early on in our discussion that density is a way for us to convert between volume and mass. Okay, so I want you to see how that works. So yesterday in our lecture, we talked about how we can use these conversion factors. I'm going to use this conversion factor because this has to do with water. And the way I'm going to use this is I'm going to think about it as this is telling me that for water, 1 gram of water is equivalent to 1 milliliter. Now, that's not super evident in the way this is written, but that's what that means. When it says 1 gram per milliliter, this is how we want to interpret it, right? And then all of a sudden, we can use that as a conversion factor. 1 milliliter of water has a mass of 1 gram. And basically what that does for us is convert us between units of volume to units of mass. And so obviously that's not a hard question. 35 grams of water is equal to 35 milliliters of water, which is kind of cool. And again, we will use that conversion later on in the quarter. So let's just say, you know, this is 35 milliliters of oil. So let's do that again. So if we did this with 35 milliliters of oil, right, we would use a different conversion factor because oil has a different density. We're going to use that one right there. And it turns out that when we put 1 milliliter of oil on the bottom and 0.93 grams on top, essentially we're going to get a different mass, right? The mass is going to be a little bit less than 35. Okay, and I don't have my calculator in front of me, but you guys can do that math, right? Significant figure-wise, if we were having that conversation, we would have 2 sig figs in our answer when you get done. So when you figure that out, you're going to put grams in here, and hopefully you guys will do that. Okay, I am going to grab my calculator because I want to do that for the next one. So pause. Okay, so I lied. Let's go ahead and do this. So we're going to take 35 times 0.93. And in my calculator, I get 32.55 grams. And because I'm thinking about significant figures, I'm going to round this up to 33 grams. So obviously, because, well, not obviously, but perhaps you can see that because the density of oil is less, the mass of the same volume of oil is going to have less mass. Okay, and that might also clarify why oil floats on water. Okay, one other sort of really impressive feature here is I wanted to show you guys how powerful dimensional analysis is, okay? So basically, before I do that, let's do the easier one. So this has, and you guys actually have an extra credit assignment that you can do for me where you actually create a density column. There's a post in Canvas in the extra credit section. And I encourage you guys to do this, and I'll tell you I do have an alternative motive. I do want you to do this at home. If you have children, if you have family, I want you to spread the science word. So if you do this extra credit assignment, I love to see videos or photos of you doing this with your friends and your colleagues and that sort of thing. Okay, so basically this is what this is asking. If we see these 4 different substances and we put them in water, the question is who's going to be on the top and who's going to be on the bottom, right? We know water has a density of 1 gram per milliliter. So I hope the logic here is that as we put these substances into the water, as you are expected maybe to do for your extra credit assignment, by looking at the density, you can tell who's going to be on the top and who's going to be on the bottom, right? So let's color code these really quick. So let's say here's the carbon tetrachloride, and it has the highest density, so we would expect it to be on the bottom. So there's the carbon tet. Then the chloroform has the second highest volume or density, sorry. So we would expect it to be next. And then let's make water blue because that makes sense. So then there's 1, we're going to put the water in between. So the water might go there, right? And then the olive oil is the next one, right? So it would sit here on top of the water. And then last but not least, we would see the heptane on top. And again, we know that because of the densities. The highest density is going to be on the bottom and the lowest density is going to be on the top. And I hope that makes sense to you in terms of how things are going to arrange themselves. Now, I'll just say kind of as a little teaser for later on, we're going to talk about something called solubility. And so some of these things you'll find, solubility, will mix with each other, okay? And we'll talk about why or why not. But as you do this experiment in your house with as the extra credit, you know, you might find that some of these things will mix. But if you pour very, very, very carefully, you might get them to separate. I don't know. I'm not going to start talking about alcohol too much because it's only like, I don't know, 8 o'clock in the morning. But if you've ever had a black and tan around maybe St. Patrick's Day where you layer 2 different flavors of beer, you carefully pour them on top of each other, you can get a black and tan. That's an example of density, and I'm always looking for good examples. Okay, now what I want to do is I want to show you the power of dimensional analysis. So this question right here, where it asks, if gasoline has a density of 0.66 grams per milliliter, what is the mass of 1 gallon reported in kilograms? Okay, so a big hard question to start off, to finish up here. So I want you to think about, you know, a gallon of milk and what it feels like to carry that. I want you to think about carrying around a gallon of, maybe you've gotten like gallons of water before. I want you to think about what that feels like, right? And so the heft, the weight, the mass, it's a gallon, obviously, because it's a gallon. And so if you think about the difference between carrying a gallon of milk, a gallon of water, or a gallon of gasoline, they're going to have different mass because they have different densities. Okay, so what we're trying to do now is we're trying to figure out what is the mass of a gallon of gasoline. All right, a gallon is a unit of volume, and we're trying to figure out how much what's its mass? What is the amount of matter in this gallon? Okay, so we said in dimensional analysis that we always start with what's given. Okay, so what's our given? And then we use conversion factors. Okay, and then we want to get to what we want the unit of our answer to be. Okay, so that's kind of how I encourage you guys to do this. So it's not apparent in this problem, but our given is 1 gallon. It's really not that clear, but there's 1 gallon of gas. Okay, our conversion factors we're going to put in together, but the first one we have right there, and the other 2 I've given you right here. So we're going to use a couple of them. And what we'd like to do is we'd like to find the mass, but we'd like it in kilograms. Right there. So I'm going to just put kilograms over here. Okay, so here we go. So again, what I'm trying to do is not scare you to death, but try to show you the power of dimensional analysis. And those of you that are taking the TEAS test, I'll just say there's a lot of students who've come to me and said, I used dimensional analysis a lot when I was doing the TEAS test. So our first sort of thing that we want to do is we're in the English measurement of gallons, and we'd like to get to the metric system. And the reason I know that is because my density right here is in the metric system. So my first thing I'm going to ask us to do is convert from gallons. Okay, so we're going to go from gallons to milliliters is what we're going to do. Okay, so I'm going to use this conversion factor right here. I want my gallons to cancel, so I'm putting gallons on the bottom, and I'm putting 3,800 milliliters on the top. And what I'm doing here is making sure that my units cancel. So I put the units always have to come down to the bottom, right? Okay, so next, now I'm in milliliters, and what I want to do now is convert between volume and I want to go to mass. And so my unit to do that is going to be this density right here. So it turns out that, again, it's hard to see this, but this says that 1 milliliter, that's what the milliliters on the bottom mean, is 0.66 grams on the top. Okay, so I've used that conversion right there to get between volume into the units of mass, right? So volume to mass. Okay, so that's cool. So I got that done. Okay, and then my next thing is I want my grams to be in kilograms. So if you remember back in the lecture yesterday, we said kilo means 1,000, right? And so we're going to convert between grams, 1,000 of them. Okay, we wanted the units to come down so we can cancel those. And that's 1 kilogram on the top. So that's what I did right there. I used that conversion factor. So what I did is I made sure that all my units cancel. Okay, so gallons went away, milliliters went away, grams went away. That's kind of satisfying. The unit I'm left with is always going to be the unit that I'm asking for, or the unit I want my answer in. And then as we spoke about yesterday, we said if the number's on the top, we're going to multiply. And if it's on the bottom, we're going to divide. Okay, and the power of this is you can do this in one fell swoop. So I can take 1 times 3,800 and then multiply it by 0.66, and then I can divide it by 1,000, and then I'm going to have my answer. So where'd that come from? There's the 1, there's the 3,800, there's the 0.66, and there's the 1,000. Multiply, multiply, divide. Okay, so let's do that. So 1 times, that's pretty easy, 3,800 times 0.66 divided by 1,000. And I get my answer that I get out of the calculator. Whoops, I want this to be black. Hold on. The answer I get out of the calculator is going to be 2.508 kilograms. And if we speak about significant figures, there's 1 So I only get to have one in my answer. And so hopefully you're cognizant of the fact that I would round this up to 3 kilograms, and that would be my answer. So we're not, I don't think, I'm not as sort of versed in kilograms, but I'll just say that just so you know, 1 kilogram is equal to about 2.2 pounds. That might help you. I don't know. But basically, you know, when you're hefting around a gallon of milk or a gallon of water or a gallon of gasoline in this case, you know, a gallon's going to be about 3 kilograms. Okay. So you've seen dimensional analysis and the power thereof. I know that it may be overwhelming for some of you, but you know, the fact that you can kind of string these guys together and quickly get to your answer is really, really, really powerful. You know, just making sure the units cancel, they always come down to the bottom, and you're always left with the unit of what you wanted to get in the end. Okay, so my last sort of moment here is I feel like next week we get to do real chemistry, but this week we're just kind of doing job training, and I just can't say enough about this sort of positive negative thing. So this is randomly thrown in here at the end, but I do want you to understand why this is something that's going to be so prevalent throughout the course, and it explains so much about chemistry. Electrostatic forces, okay, basically positive and negative forces. I know you guys are probably too young to remember who Paula Abdul is, but if you look her up and you look at Opposites Attract, there's a funny song, but you know, it was in the 80s or something like that. So basically, I think you guys probably know this, right? That if I put a positive and a negative charge together, that they attract each other. That if I put a positive and a positive or a negative and a negative together, they repel each other. And this concept is crazy important, and yet it's not really understood by scientists. This is what we call a fundamental property of matter that isn't really easy to explain. So basically, we understand that these forces, when you have opposite charges, they attract each other. And again, so much chemistry is determined by this, and so that's why I'm putting this out here in the very beginning. Like charges repel, okay? So you could say opposites attract. Okay, like charges repel. Okay. And then it's interesting to understand like the size. So one of the other things I want you to get is if I make a bigger positive and a bigger negative, there's going to be more attraction. Okay. If I make a bigger positive and a bigger positive, there's going to be more repulsion. So the size matters. Okay, so basically as I increase the charge or decrease the charge, the attraction or repulsion can increase or decrease. The other thing that I want you to understand is that if I put the charges close together or if I put them far apart, distance matters, okay? So if they're close together or they're farther apart, the closer, the greater the attraction or repulsion. Okay, and if they're farther apart, more distance equals less attraction or repulsion. Okay. And all of those things are going to manifest in a lot of chemistry. And so I always like to kind of throw this out here at the very beginning. It does seem very random, but again, it will be something that will come up over and over and over again. Okay, so that takes care of our second lecture. Again, going back to the objectives on here and making sure you're good with that, making sure that you're checking in on the reading for this chapter. So I would definitely go back and look at that. Thank you guys so much for your attention, and I hope you're having a great weekend. Thank you so much for a productive, I hope, first week of the summer quarter, and I will see you guys next Tuesday. Have a great day. Bye.